Welcome to the lecture 3 of the course Computer Organization and Architecture. So basically in this lecture we'll be discussing the various performance aspects of a computer. So 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 with respect to performance, the speed of execution of programs is very important. So we measure the performance of a computer on that basis, like how quickly a computer can execute programs. So based on that, we say that whether the performance is high or low or what. Okay. So how to measure that? What are the various metrics available to measure the performance of the computer? So that's what we are going to discuss in this lecture. So so as we have said already, so how quickly a computer can execute programs? This is a crucial question which needs to be answered, and 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 that cannot be and that and that does not depends on one factor. Actually, it depends on several factors. So speed of execution basically depends on all the hardware components of the computer, because as we already discussed, different hardware components works at different speed, and also it depends on the machine language instructions. Why it depends on the machine language instructions? Because finally, when a user write a program, the user writes the program in the high level language. Then then the compiler converts the program to the machine language instructions. Okay, so finally, the program has how many machine language instructions? Based on that, the execution will differ. Okay. So if there are less number of machine language instructions, then the program may execute quickly. If there are more instructions, probably it may take more time. And also, the speed of execution of the computer also depends on the performance of the compiler, right? Because compiler is the one which converts high level language to machine level language. So there is something called an optimized compiler. An optimized compiler is the one which converts the high level language to as reduce high level language to corresponding machine language instructions such a way that then the number of machine language instructions will be as low as possible. For that, what are the different things that are possible the compiler will do? Okay. So such a compiler is called as an optimized compiler. So the role of all these three components are crucial: hardware, machine language instructions, and compiler for deciding the speed of the execution. Right. So the best performance will be achieved when there is a proper design coordination between all these three units: processor, machine instruction set, and compiler. So when you take any program which is being executed, initially the program will be in the main memory, and then depending on the requirement, when the program is getting executed, the respective instructions and data that are stored in the main memory uh, will be moved will be the processor will fetch the instruction from the main memory one by one. Okay, and then it will keep it in the cache. Okay, only for the first time, when a particular instruction is executed for the first time, then the CPU will fetch that instruction from the memory, and then it will store in the cache. If the same instruction is to be executed for the second time, then the processor will not look into the main memory, rather it will access it from the cache itself. Because as we know that processor can access the cache at a faster rate. And in most of the computers, processor and the cache will be in the same chip. So which is called as internal cache. Right? Okay. So, so the, the performance will increase to the extent the the movement of instructions between processor and the main memory is reduced. So our objective is to minimize the movement of instructions between processor and main memory. That is, keep as much as required information in the cache, so that it will not be required for the processor to fetch something from the main memory. So the processor will fetch something from the main memory only if the data is not available in the cache. So, so, so if we are able to reduce the amount of communication between processor and main memory, then obviously the performance of a computer will increase. For example, in a typical program, if you take the execution of a loop, say a loop is executing for 100 times. During the 100 times, it is going to execute the same instructions. So if these entire loop instructions are moved to the cache, then the processor will just fetch it from the cache. So for all such instructions which will be repeatedly used, that should be moved to cache. So it's not only loop, any data or any instructions which will be required by the processor for several times, which will be used repeatedly. Such info should be available in the cache so that there can be improvement in the performance of the computer. So this is the introductory part. Next, we'll try to understand what is a processor clock. So, so you might have heard the term clock several times. So clock is basically a timing signal. Clock is basically a timing signal. Okay. The duration of one clock cycle, we are denoting it as P. Okay. We are denoting it as P, which means period. Some of the books may call it as T, but here we are using the terminology P. So here you can see a sine wave. So this is one clock cycle. Starting from here to here, this is one clock cycle. So the time duration between this point and this point, we are calling it as P. Okay. So the period or the time duration for one clock cycle, we are calling it as P. So this is an analog signal, whereas this is a digital signal. So in a digital signal also, this is one clock cycle. This is one clock cycle. Okay. So this period for one clock cycle, we are calling it as P. Okay. Then there is something called as clock rate. We are representing clock rate as R. We are representing clock rate as R, which is equal to 1 by P. Clock rate is nothing but R, which is equal to 1 by P. So 1 by P is nothing but clock rate R, and that is called as number of cycles per second. So here this one represents 1 second. Okay, so T represents the duration of the one clock cycle. So this will be less than a second. Okay, this will be surely less than a second. So 1 by P represents number of cycles in a given second. Number of clock cycles in a given second. Okay. For simplicity, let us assume that this P value is 0.25. This P value is 0.25. Okay. So then what will be, so P is 0.25 means what will be R? R will be 1 by P. R will be 1 by P, that is 1 by 0.25, which is nothing but 4. It means there is 4 clock cycles in 1 second. Okay, that is what cycles per second. In 1 second, how many clock cycles are there? 4 clock cycles. Okay, and this is the cycles per second. Normally, we also call the cycles per second as heads. Okay, so it can be called as heads. So the clock rate is, in this case, if P is equal to 0.25, then the clock rate is 4 heads. Okay, if P is equal to 0.5, if P is equal to zero point 0.5, okay, then the clock rate R will be equal to 1 by zero point 0.5. So 1 by zero point 0.5, which is nothing but 2 heads. It's nothing but 2 heads. Okay. So this is how the clock rate is calculated. Okay. So generally we used to hear the terms like this. The processor is working at 500 megahertz clock cycle, 1.25 gigahertz. Like that we used to hear. Okay. So this megahertz, gigahertz are nothing but what? These are cycles per second. How many cycles per second? So there are 500 megahertz of cycles per second. Okay, 500 megahertz means how many hertz? Okay, so see 1000 hertz is 1 kilohertz. Okay, 1000 hertz is 1 kilohertz, and 1000 kilohertz is 1 megahertz. So 500 megahertz is equal to how many kilohertz? It is equal to this much kilohertz. Is equal to this much kilohertz because you have to multiply by 1000, right? Because 1000 megahertz is 1000 hertz is 1 kilohertz, 1000 kilohertz is 1 megahertz, 1000 megahertz is 1 gigahertz. Okay, so 500 megahertz is equal to this many kilohertz. Okay, and it is equal to how many hertz? So it is equal to 5. This is again three zeros. Okay, and again three zeros. So it is equal to this many hertz, right? It is equal to this many hertz. So then you see how many. So it means that this many clock cycles are there in 1 second. So this many clock cycles, 5 followed by 8 zeros. This many clock cycles are there in 1 second if the processor is working at a speed of 500 megahertz. Is it clear? Okay. So if it is 1.25 gigahertz, then what is that? Okay, you can calculate, right? Okay. So for 500 megahertz, the clock period is 2 nanoseconds. That is P. If okay, if what you call if if the if the clock rate is 500 megahertz, then the value of P is 2 nanoseconds. Okay? If the clock rate is 500 megahertz, then the value of P is 2 nanoseconds. Okay? If the clock rate is 1.25 gigahertz, then the value of P is zero point 0.8 nanoseconds. Okay, so that means one clock cycle it is 2 nanoseconds here for 500 megahertz clock rate. For here, one clock cycle is only zero point 0.8 nanoseconds. Okay, so if for example I gave say the clock period is 2 nanoseconds, calculate the clock rate. Okay, in terms of megahertz, then how will you do that? Okay, how will you do that? Any idea? Let us, I'll give an example. Say for example, say, okay. So let us take this 2 nanoseconds. See, so it means that one clock cycle takes only 2 nanoseconds. That is, one clock cycle takes only 2 nanoseconds. Okay, so in 1 second, how many such 2 nanoseconds are there? First, we should know that. So in 1 second, how many such 2 nanoseconds are there? Okay, fine, are you getting? So one clock cycle takes 2 nanoseconds. So in 1 second, how many clock cycles are happening, or how many 2 nanoseconds are there? Because each clock cycle is for 2 nanoseconds. Okay. So for that, first we should convert 1 second, 1 second to nanosecond. Okay. How will you convert 1 second to nanosecond? 1 second is how many milliseconds? 1000 milliseconds is one second, right? Okay, this many millisecond, 1000 millisecond is 1 second. And how many microsecond is 1 second? This many microsecond. Add another three zeros. This many microsecond is 1 second. Okay, now we want 1 second in terms of nanosecond. How many nanosecond is 1 second? Again, add three zeros. Okay, so this many uh, nano nanosecond. I'm not sure I added correctly or not. Let me continue. See, 1000 millisecond is 1 second. Again, add three zeros. This many microsecond is 1 nanosecond. Again, add three zeros. This many nanosecond is one. This many nanosecond is 1 second. Okay. So this many nanosecond is equal to 1 second. Fine. Now each clock cycle is for how many nanoseconds? 2 nanoseconds. So how many cycles are there? Divide this by 2. Divide this by 2. This many cycles. Okay, this many cycles. So it means the clock. This is the clock rate. This is nothing but the clock rate R. We have identified the answer. But this answer is in terms of heads. This many heads. The clock rate R contains this many heads. Okay. So, so this many heads. So how many kilohertz does it have? Divided by 1000. So this many kilohertz. This many kilohertz. Okay. How many megahertz it has? Again divided by 1000. Okay. So it has this many megahertz. Right. Okay. I think it's clear. Similarly, you can work out for zero point 0.8 nanosecond also. Say, okay, let me do that. So again, one second contains 1000 millisecond. Okay, and it has this again add three zeros. This many microsecond is equal to 1 second. Again add three zeros. This many nanosecond is equal to 1 second. Now the t, that is one clock cycle, is zero point 0.8 nanoseconds. So how many clock cycles will be there in 1 second? Okay, so divide this 1 second. This is nothing but 1 second in terms of nanosecond. Divide this by zero point 0.8. When you divide this by zero point 0.8, what you get is this value. Okay, so the clock rate is nothing but this much heads, this many heads. But we want the answer in gigahertz. Okay, so if you divide it by 1000, you will get it in kilohertz. So this many kilohertz. Okay. Again, if you divide it in 1000, divided by 1000, you will get it in megahertz. So this many megahertz. Again, if you divide it by 1000, you will get it in gigahertz. So this many gigahertz, 1.22 gigahertz, right? Okay. So now I think if the clock period is given in terms of nanoseconds or microsecond or millisecond, and if you are asked to calculate the clock rate, I guess you can calculate, right? So this is how the clock rate is calculated. Right? So, so processor clock is one of the crucial factors in deciding the performance of a computer. So that's what we are discussing this. Next. So the basic performance of a computer is given by this equation. T is equal to n into s by r. Okay. So let us understand what is T, what is n, what is s, and what is r. The T is the processor time required to execute a program. To execute a given program, how much processor time is required? So that is called as T. Okay. And n is the actual number of machine instructions required to execute the program. Okay. See, this is not, here there is a small catch. N is the actual number of machine instructions required to execute the program in the given round. Okay, it is not that how many machine instructions are there. That is not the point. Okay, for example, assume there is one particular source program. Say SP is a source program. The compiler converts it to a machine language program. Say the machine language pro, uh, machine instruction, there are 100 statements out there, 100 instructions out there. Okay, but when the user is executing, depending on the user input, some of the instruction may not be executed. Okay, say for example, there is a if statement. Then if the if is true, then the true part will execute. Otherwise, the else part will execute. Okay, or the loop. The loop will depend on the loop control variable. Okay, if that is so, so the point I mean in the sense, it is not that all the machine instructions should be executed. The number of instructions that get executed may depend on user input and on other several other factors. Okay, so this n represents actual number of instructions that is executed. Okay, so when this program is executed in one particular round, out of 100 instructions, only 80 instructions may be executed. Remaining 20 might not be executed, maybe because of if statement, or the or due to some other reason, some statements might have been skipped. Okay, so n, so that is what n. So here n is not 100, n is 80. That is, when you execute this program, how many instructions you are using. The unused instructions we won't count. So that is called as n. Okay. And yes is the average basic steps needed for one machine instruction. What is that basic step? See, assume this is the first instruction, but this first instruction, when you execute, it may need two operands. So you fetch the instruction from the memory to the processor. After that, it is asking for two operands, operand 1 and operand 2. So again, you fetch operand 1, again you fetch operand 2. Then only the operation can be done. So this fetching of operand 1 and this fetching of operand 2, this is called as basic steps. Okay. So this particular instruction, it has two basic steps. Like the different instructions will have different number of basic steps. Okay. So so yes is the average basic steps needed for one machine instruction. That is, for all the instructions, you calculate what are the basic steps and take the average. Okay, so the average uh, basic step needed for one machine instruction. Okay, and each basic step will take only one clock cycle to execute. So you should be very clear. The basic step only will take one clock cycle, but each instruction may take more than one clock cycle. Because if you see this instruction, as I said, you are fetching this instruction. Again, it needs two operands. Fetch operand 1, operand 2. Again, perform calculation. So all these things put together, this instruction may take 3 or 4 clock cycles. This instruction may take 3 or 4 clock cycles. But uh, so this is only one instruction. It doesn't mean that one instruction will take only one clock cycle. No, because one instruction contains many basic steps, right? So, but each basic step will take only one clock cycle. Not each instruction will take one clock cycle. Okay, is it clear? So, so each instruction will have, if you take one particular instruction, this instruction may have, say if this instruction has three basic steps, then it will take three clock cycles. Okay. So it is not that each instruction will take one clock cycle. No, each instruction can take more than one clock cycle, but each basic step will take one clock cycle. Okay. Then T is given like this, N into S, right? Okay. So here to improve the performance, our objective is to reduce the T. Because T is the processor time. So time for execution should be reduced. Then we say that okay, speed is increasing, so we should reduce the speed. Okay, to reduce the, uh, I mean to to execute faster, we should reduce T. If you want to reduce T, then N and S also should be reduced, but R should be increased. So this is our objective. Our objective is to reduce T, so reduce N and S and increase R. Okay? So, so how to do that? Okay. So N is reduced. So N is nothing but number of instructions that is executed. Okay. So N is reduced if the compiled program contains fewer instructions. So if you are using an optimized compiler, then N can be reduced. So here comes the role of the compiler. If you are using an optimized compiler, then N can be reduced as much as possible. Okay. S is reduced if there are less number of basic steps. If there are less number of basic steps, if the average basic steps is less per instructions, then S will be reduced. There is another way to reduce S, which is important, which is called as overlapping instructions, which is also called as bytecode. Right? This is crucial. There is another way to reduce S. The first way to reduce S is to reduce the number of basic steps. The another way to reduce S is overlap the instructions. Overlapping means, say it is something like concurrent execution. That is uh, when when the first instruction is performing one operation, the next instruction can perform another operation. So that is called as overlapping instructions. Okay. So for example, see see, in any instruction execution, normally we follow this pattern. Instruction fetch. Okay, I'll call it as IF. Instruction fetch. Okay, that is fetch the instruction. Instruction decode. Instruction fetch means the instruction will be moved from memory to processor. Instruction decode means the processor will decode the instruction and understand what is to be done. Then operand fetch. If the instruction needs some operands to be fetched from memory, it will be fetched. Okay. Then execute the instruction, and then store the result. Okay, these are the steps which are required in any typical instruction. Okay. Now, say the first instruction is fetched. Okay. So this instruction fetch will be done by one unit. Decoding will be done by another unit. Operand fetch will be done by another unit. Okay, execution will be done by another unit. Storing will be done by another unit, another functional unit of the computer. So all these are different units. Okay. So what happens in the sense, the first instruction is fetched, and it is fetched and it is in the decoding state. When the first instruction is getting decoded, what you can do, when the first instruction is getting decoded, during that time you can fetch the second instruction. You get it? So because this unit is free now. Similarly, after decoding, the first instruction will go to operand fetch. So when the first instruction is in the operand fetch stage, the second instruction can be decoded. Okay, and the second instruction is decoding currently. Okay, if the second instruction is decoding, uh, then the third instruction can be fetched during this period. Okay, so this task is called as pipelining. So by pipelining, what we are doing is we are overlapping the instruction execution. By this also, the effective value of the OR will be reduced. Sorry, effective value of S will be reduced. Okay, how is that? Later also we'll discuss with an example. The time being to understand this much. Okay, and the another way, and the another parameter is R. R should be increased. How can we increase R? So to increase R, you have to increase the clock frequency. Okay, but increase clock frequency means what? So say that clock frequency is 2 nanoseconds. It means that one clock cycle takes 2 nanoseconds. So increasing clock frequency means, if you make this to one, or it is currently 2 nanosecond, but if you make it to 1 nanosecond, then what is the meaning? If you make it 1 nanosecond, the meaning is one basic step should be completed in 1 nanosecond. You get it? So because how we define a basic step? The basic step is one which takes only one cycle to complete. Okay. So if you are able to do a basic step in 1 nanoseconds, then we can increase the clock frequency. Otherwise, you cannot increase the clock frequency. So increasing the clock frequency means the time required to for one basic step should be reduced. Okay. So N, S, R, all these are dependent. So N is the number of machine instructions, or S is the average basic steps, and R is the clock frequency. All these are dependent. When you change one, the other value will also change. Okay. So normally the vendors, when they sell the processor, they sell it by using the clock frequency. They always say that this processor works at this clock frequency. It works at 1 gigahertz. It works at 3 gigahertz. It works at 5 gigahertz, like that. So by saying that, they mean that it performs better. Okay, but as a computer engineer, you should not get attracted towards that, because see this statement: a processor with a 900 megahertz clock, a processor with a 900 megahertz clock need not be better than a 700 megahertz clock. Okay, because this is what this is R. 900 megahertz clock means what? It is R, clock cycle, how much clock rate required. This is R. But the processor speed performance is not only dependent on R, it also depends on N and S. Okay. Say for example, a processor with a 900 megahertz clock have a high value of S, and a processor with 700 megahertz clock has a less value of S. Then obviously the processor with 700 megahertz clock may perform better than 900 megahertz clock. Okay, where S is the number of basic steps for average number of basic steps for each instruction. You get it? So, so this is an important point which you should understand. Next. So next we'll be discussing something called as pipelining and scalar operation. So what is meant by that? So pipelining and superscalar operation. Okay. So let us consider this instruction: add R1, R2, add R1, R2, R3. So what this instruction will do in the sense, it will add R1 and R2, and it will store the result in R3. It will add R1 and R2, and the result will be stored in R3. Okay. So here with this instruction, let us further understand pipelining. Okay. So now ALU is going to add, arithmetic and logical unit is going to add. So other part of the processor will be free during that time. Okay, so while R1 is getting added to R2, during this time, the processor can read the next instruction from the memory. Okay, so what happens in the sense, while addition is going on, during the same time, next instruction is also fetched. Next instruction is also fetched. This is happening parallelly. Okay, so this is one step. Next step, while writing to R3, finally the result will be returned to R3. So when the result is returned to R3, when the result is returned to R3, during that same time, during that same time, the operands of the next instruction can be moved to ALU. Okay, because next instruction you fetched already. Now after that you have to decode and fetch that data for that instruction, and that data can be moved to. So move the data of the next instruction to ALU. Okay, the next instruction, the data corresponding to the next instructions can be moved to arithmetic logic. Okay, so now what happens? See when the add is happening, when the first instruction is adding, you are fetching the next instruction. When the first instruction is storing the result, during that time, the data corresponding to the next instruction is moved to arithmetic logic unit. Okay, so this is called as pipelining. This is called as pipelining. So this is possible if you have a sufficient number of functional units to perform these operations. Okay, if you have sufficient number of functional units to perform this operation. Okay, so now what happens in the sense, the time required, now the effective time is getting reduced. Now the effective time is getting reduced. Okay, so so this also means that instructions need not always execute one after another. Instructions are not necessarily executed one after another. Here actually, in your program, maybe this is the first instruction and this is the second instruction, but in internally that is not happening. You are zigzagging the execution as long as the output does not change. Okay, so the processor is allowed to change the execution order also, but only thing it should ensure that the output should not change. Okay, okay. Here there is an important line. The value of S does not have to be the number of clock cycles to execute. Uh, have to be the number of clock cycles to execute one instruction. Okay. So what does it mean? So what is yes? So yes we defined as the number of basic steps required for one instruction. Okay. This is the number of basic steps required for one instruction. Okay. So mm, assume that there are two instructions. Say instruction one. Say instruction one. So this instruction one has two basic steps. Instruction one has two basic steps. Okay. Basic basic steps. Say instruction two. There is another instruction, instruction two. Say instruction two also has two basic steps. Instruction two also have two basic steps. Okay. Now Now the point is, if these two instructions were executed sequentially, let us try to understand if these two executions executed sequentially, what will happen, and if these two instructions executed using pipeline, what will happen. Okay. So if these two instructions execute sequentially, what will happen in the sense, for the first instruction, there are two basic steps. So obviously it needs two clock cycles. Okay. And for the second instruction also there are two basic steps. So it also needs two clock cycles. Now what is the average value of S? That is 2 plus 2, 4. 4 by 2 is 2. S value becomes 2. Okay. Okay. So that is what the statement means. The value of S doesn't have to be the number of clock cycles to execute one instruction. Here the value of S is equal to the number of clock cycles required to execute one instruction. Okay, because each instruction needs two basic steps, so it needs two clock cycles. Okay, this is for serial execution. But assume the processor supports pipelining. So as it is supporting pipelining, what happens in the sense? Say when instruction one is performing basic step one, the processor is executing the basic step of, I'll call it as BS. BS one of instruction 1. Okay, during the same time, the processor may also execute the basic step 1 of instruction 2. Okay, now what happens? During one clock cycle, you are performing two operations. What are the two tasks? Basic step of 1 also executed during the same clock cycle, say T0, and basic step 1 of instruction 2 also executed during the same clock cycle T0. So during T1, basic step 2 of instruction 1 is executed, and also basic step 2 of instruction 2 is executed. Okay, so 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 this is called as pipeline, right? This is called as pipeline. So when basic step 1 of instruction 1 is executed during the same time, basic step 1 of instruction 2 is also executed. And basic step 2 of when basic step 2 of instruction 1 is executed during the same time, basic step 2 of instruction 2 is also executed, right? So this scenario is called as a pipeline. Okay, so now what is the value of yes? See, mm, in the previous case, when it is executed sequentially, first instruction needs two clock cycle, second instruction also needs two clock cycle. Okay, but now if you see, both instructions has completed in two clock cycle. Both instruction has completed in two clock cycle, because the T0 is one cycle, T1 is another cycle. But during this time, you have completed two instructions. So now what is the value of yes? Yes is the average number of number of basic steps, average number of basic steps required for each instruction. Okay, where what is the basic step? The basic step is how many clock cycles are required. Okay, for how many clock cycles are required for each instruction. Okay, so so in this case, so S is the average basic step needed for one machine instruction. Okay, average basic steps needed for one machine instruction. Okay, so so even though there are four basic steps, but all these four basic steps are are completed in two clock cycles. Okay, all the four basic steps are completed in two clock cycles. So it means that two instructions got executed in two clock cycles. Okay, so how much time it will take? Two instructions. So the point is two instructions completed in two clock cycle. So how much clock cycle will take for one instruction? It is one. So by that yes will become one. Are you getting? Two instructions you are completing in two clock cycle. So for one instruction it will take how many clock cycle? Only one clock cycle. So the effective value of S is reducing. But here that is not the case. For two instructions you are taking four clock cycles. So for one instruction how many clock cycles? Two clock cycles. Right? So this is how the effective value of S can be reduced. So that is what this line says. The value of S doesn't have to be the number of clock cycles to execute uh, one instruction. Uh, okay, it may when you use pipelining, the things may change. So pipelining is overlapping the execution of successive instructions. So if the computer is more powerful, then you can execute multiple instructions, multiple instruction pipelines are implemented in the processor. That is, multiple instructions can be pipelined. So in the previous case, we discussed pipelining two instructions. If you pipeline four instructions, five instructions, then what will happen? Then obviously S value will reduce. Okay. So the ideal value for S is 1. The ideal value for S is 1, which means what? Again, go back to the definition of S. S is the average basic steps needed for one machine instruction. Okay. Average number of basic steps needed for one machine instruction. So, mm, so where each basic step needs only one clock cycle. Okay. So where each basic step needs only one clock cycle. So if S is equal to 4, and if it is serially executing, in each instruction will take 4 clock cycles. Okay. So the ideal value of S is 1. If S is equal to 1, then it means that each instruction is having only one basic step. If S is equal to 1, it means each instruction is having only one basic step. And by that, what will happen in the sense, each instruction will execute in one clock cycle. Because if there is only one basic step, then it will execute in only one clock cycle. Okay, but is it possible practically to have only one basic step? No, that is not possible. But pipelining is possible. By pipelining, what will happen in the sense the effective value of S will reduce. You getting? By pipelining, the effective value of S will reduce. When you execute serially, there may be uh, four basic steps, but you are using pipelining. So when you use pipelining in each clock cycle, you may be executing 2-3 instructions. Okay, so obviously the effective value of S will come down, right? So, the ideal value of S is 1. Practically, that may not be possible, but by using pipelining, we can reduce S such a way that we can make S to approach 1. Right? And the goal is to reduce S. Okay. So, if the computer is supporting superscalar operations with multiple stages of pipelining, I mean with multiple instruction pipelining is possible, then yes, may also go less than one. Okay, very rarely. Then we will see like how to increase R, how to increase the clock rate R. So the clock rate R can be increased. There are two ways to increase the clock rate R by improving the IC technology to make the circuits faster, so that the circuit works faster, and by that you can increase the clock rate. Okay. So when you increase and there is another way to increase the clock rate by reducing the amount of processing done in the basic step. But if you reduce the amount of processing done in the basic step, then the number of basic steps may increase. Okay. So this second option is not an correct option. So the only so then we can say that the only way to improve the clock rate is by improving the AC technology. Okay. So when you improve the, so it is not. So when you improve the IC technology, uh, it means that one basic step can be done in less time. That is what we mean. One basic step can be done in less time. Previously, if one basic step can be done in 2 nanoseconds, and if you increase the IC circuit in such a way that one basic step can be done in 1 nanosecond, then the clock rate is improved. Okay? So by increasing the R, the entire processor's operation also will equally improve, except the main memory. Okay, because compared to processor, main memory is a slower device. Then the speed compensation should be done by using cache. This is how we can increase the clock rate. Then there are two types of computers. One is called as CISC, the other one is called as RISC. CISC is called as the complex instruction set computers, and RISC is called as reduced instruction set computers. Okay? And and the and there is a and these are and there is a trade-off between, and this CISC and RISC can be, what do you call, it can be treated as a trade-off between N and S. What is N? N is the number of machine instructions to execute a particular program in a given round, and S is the average number of basic steps for an instruction. Okay, so previously we discussed that we can bring S close to 1. Okay, even though the number of basic steps per machine instruction may be considerably large. So this point you should understand. I don't know uh, how much you are able to catch it. That is, S is close to 1. That doesn't mean that the number of basic steps will be equal to 1. No, by using pipelining, the effective value of S will come to 1. Because when you use pipelining, more than one instructions were executed in pipeline fashion, so the effective value of S will be reduced. Okay, so when so S is close to, so you can bring S to close to 1, even though the number of basic steps may be larger. Okay, So it is much easier to implement efficient pipelining in processor with simple instruction set than in complex instruction set. Okay? So there are two types of computers. One is complex instruction set of computer, another one is simple instruction set computer. So in complex instruction set computer, what happens in the sense you will have a complex instruction which you can, for example, to perform a particular task in a simple instruction computer, if you are using five instructions, that can be done by just one instruction in a complex instruction set computer. But this one instruction will be complex. It may perform several operations. But here that one instruction is splitted to five instructions. You get it? So so when compared to CISC and RISC machine, actually RISC with pipelining will produce better result. Okay, it is much easier to implement efficient pipelining in processor with simple instructions. Simple instruction, reduced instructions. Okay, because even though there are five instructions, that is S value is five. That is each instruction has five basic steps, but you have pipelining. With pipelining, the effective value of S is reduced. Okay, but here even though you have one instruction, but this one instruction may take more than one clock cycle or three, four clock cycles. So that's what we are trying to say here. Next is compiler. So, so the role of compiler is also crucial in deciding the performance of the computer. So the compiler is the one which translates the high-level language program into machine instructions. So to reduce n, it is to reduce the number of instructions that will be executed in a given round. We need an optimized compiler. So the optimized compiler is the one uh, which produced as reduced machine instructions as possible. So the goal is to reduce n and s. So, but actually, when you see compiler is not may not be designed for a specific processor. But if you want a high quality performance from the compiler, then the compiler should be concerned about the processor. So it is not that if you write a compiler for one processor, it will give better result for another processor also. No, the compiler that is written for one processor may not give that good performance in other processor, right? So the compiler should be designed for specific processor actually to get better performance out of the computer. Okay. So finally, what we are discussing in the sense, so the performance measurement basically to measure T, the time required for a computer to execute an instruction. But computing with T is not that easy. So whatever we have understood till now, it is not that easy. It involves several parameters. Okay. So the computer engineers and scientists, what they thought is it is better to measure the performance of the computer by using some benchmarks. Benchmarks means what? Already you know that there is a powerful computer. Okay. So there is a powerful computer, PC1. We know, everybody know that it's a good computer. So say all the scientific community agrees that it's a good computer. Now we are manufacturing a new computer, PC2. Okay. Now when you want to compare the performance of PC1 and PC2, just you compare PC1 and PC2. You take some 10 programs. Okay. You take some 10 programs, execute all these 10 programs in PC1 and calculate how much time it takes, and then execute in PC2 how much time it takes, and then you can benchmark with respect to PC1. What is the performance of PC2? Is it increased or decreased, or is it matching that like that? So that is called as measuring the performance using benchmark. So this is a benchmark computer, which we already know. Then compare with that. So how to do that? That we will discuss here. So measuring performance computer using benchmarks. So there is a non-profit organization called System Performance Evaluation Corporation, SPEC. Okay. They select and publish results for many commercially available computers based on this benchmark study. So for general purpose computers, a suite of benchmark uh, was uh, was published in the year 1989. Again, it is modified and published in 1995 and in 2000. And the reference computer used were, reference computer is the is the one whose performance is already known. The reference computer used was Spec 95, that is during the year 95. The one which is published in 95, for that, the reference computer used was Sun Spark 10/40. This is the computer name. And for one that is published in 2000, Spec 2000, the reference computer used was Ultra Spark 10. Okay? So let us see how to measure the performance of a computer using this benchmark. It is given by this formula. The spec rating is equal to running time on the reference computer divided by running time under the test. That's it. You take a particular program, say program 1, execute that in the reference computer. That is the standard benchmark computer. Execute in that. Measure the time, how much time it takes. Okay. Say time T1, and execute the same program in the new computer which you want to test the performance. And what's the time? T2. T1 by T2 is the speculative. Okay. So this is a simple formula, and this is generalized like this. So this is for one program, but with one program, you cannot decide the performance. So you take a set of programs. Say we take n programs. Okay, I is equal to 1 to n programs. For all these n programs, calculate the spec rating. For all these n programs, so spec I is nothing but the spec rating of first program. Spec I is nothing but the spec rate of ith program. Like that, you calculate from the first program to nth program, calculate the spec rate, and take the uh, calculate the spec rating for for all these programs, okay, and and calculate like this. Okay. So this is the formula given. Okay. So, yeah. So this is how we calculate the spec rating. So this 1 by n is nothing but the square root. Okay. So 1 by n is nothing but the square root. So using this formula, the spec rating can be calculated. Say for example, uh, say for example, for when you calculate spec rate for one particular program, say the reference computer, say say so the spec rating of, for example, if you get a value of uh, 50. Okay, the spec rating value is 50 means the computer under test is 50 times fast as the reference computer. Okay, so that's the way. Right? So that's it about performance measurement. So let us stop here. Thank you.